Okay, thank you. I would say, we always say Paxson-Sullivan instead of. Paxson-Sullivan measure. Okay. We're always considering a compact, smooth, remaining manifold with negative sectional curvature. And yesterday we introduced a class of measures on the boundary of the universal cover of this M. Okay? So this is called the measure. Is a class of measures such that you will have these two properties, because we will use this today, so it's better to recall it. You have beta belongs to gamma, the fundamental group, and then this guy equals to just beta act on mu. Okay, this is the first point. And the second thing is that if you compare these two measures on the boundary with different from different observation point, this y and the x. So the Radon-Nikodym derivative of this guy, this one is e to the power minus v. V is the volume entropy. And in our case, since we are in the negative curvature case, this v is the topological entropy. So here you have the Boltzmann function. So this is what we have, and also this family is unique if we normalized by the condition, I will put it here, is that assume this one with respect to the volume x equals to 1. Okay. So what is this new x? We already mentioned this lots of times, so we can mention it again. So this is mu x actually is the Hausdorff dimension of the Hausdorff measure on the boundary you visualized from the observation point of x. That's exactly right, roughly. That's the meaning. And now today we want move on from this Paxson-Sullivan measure to go to dynamics. By dynamics, I mean measures which are invariant by the geodesic flow. So that's the one topic we mentioned yesterday, is about the entropy of invariant measures of geodesic flow. Okay, so today this is B, part B of yesterday, and now we begin with P prime about it. And the maximum entropy measure is called the Bowen-Margulis measure. Okay, so I begin by recalling the Gromov product. We will use that for x, and the Gromov product, this guy, it's the same definition, I think, maybe. So let me finish it first. I dx z then minus dz. Okay, this is this one. So that means the geometric median is more or less the distance from x to the geodesic of this eta and Kasi. Okay, this. Then I will use this relation, the equation relating this Boltzmann function and the Gromov product. So I put it here. So I will leave it as an exercise. But maybe you don't need to do the exercise because you already see it, maybe. Okay. You have xy and eta and Kasi. Okay. So this one must be x. Okay. Then plus 2. Equals to 0. You just let x prime and y prime going this way, and then you write down the definition. Okay, so we will use this relation. And now, what's our motivation? We want to construct an invariant measure for the geodesic flow, which corresponds to the topological entropy. Okay? Then how you construct this measure? If you have a very good coordinate chart, and say if the coordinate chart are so nice, you can basically express the measure as the product. Then that's the way you see this measure. That's the optimal situation. So actually, we have such picture. In some sense, because remember in the negative curvature case, actually for the tangent space of SM, at each point you can split your tangent space into 3 directions. One corresponds to the flow direction, right? And you have one contraction, not one contraction, I mean, you have the contraction direction, and you also have the uniform expanding direction. They're almost symmetric. So more or less, we are using that chart, but we can use that in an even simpler way, is that the question is, now actually you can use the Hopf coordinates. For the geodesic flow. So what does it mean? If you have a unit tangent vector, and how you determine the position of this V? So you find it. So one way, actually, the coordinate is like this. You have your V here. So you have a unique geodesic starting from this point. So you are moving in this direction, so the Kasi will equals to the geodesic, starting with this initial speed V, going to the infinity boundary. Okay, so we will have this eta corresponds to the other direction at the point at the boundary. Okay. But still, you need to know where this V, the base point of this V, is on this geodesic, right? So how you find it? You only need a reference point X, and then you can measure actually, it's the same as that you fix a reference point, you decide where is this X naught. So you will use the Boltzmann function at V, evaluate the value at x naught. Okay? So let me put these coordinates here. This system is you have m tilde 2 corresponds to these two directions, two ends of this geodesic. But these two are not the same, right? Okay, they are not the same. And your coordinates is like you have V, you go to this geodesic, this is plus infinity, and this is V minus infinity, and so, and this is the Boltzmann function. You evaluate the value at reference point x. So this is the Hopf coordinates, okay? And now you construct the measure. You already know one direction. With this chart, it's more or less as the contraction direction, expanding direction, and also the flow direction. So you already know the measure in this direction has to be dt, right? No problem. And how about the other two directions? It should be symmetric, so it's a kind of product. So, okay. So now we need to define a measure. Mu m tilde 2. Okay? So how you define it? So locally you have this split. Of course, if you have you are at x and the one corresponds to the topological entropy thing actually we will use is this Poisson-Sullivan thing. Why? So you're back to here. So if you, okay, I haven't finished. It's not that one. We have to do something, okay? So you see a candidate of this in the expanding direction or in the contraction direction should be symmetric. So you see this is a candidate. Why? Because if you move your y, you compare your new y with new x, that this y in the geodesic starting from x going to c. Say, for example, if you are, your y is gamma v or gamma x c t. Actually, what's the contraction ratio or the expanding ratio is just a minus v and times minus t. So it's e to the t, right? That's, in some sense, why this Poisson-Sullivan measure will appear. But this, you cannot define the measure in this way. Why? Because it's a measure you need to move nearby. Of course, you cannot just put x here. That's one reason, right? Also, you want your definition to be independent of the x you choose. So here, x does not need to be the base point of v, okay? So actually, you can pick arbitrary x, and you have this product, and so you have to put some density here to make it invariant, a real measure for our purpose. So what's the candidate here is e to the power minus 2v, the Gromov product at x. Okay. So we define this measure in this way. Not proof. We need to show this nu is independent of x. Right? So this is one thing we want to do, and this is just computation using the fact, the second formula. So then you will have this the mu, let me put it here. So you change to y and you compare these two. E to the power minus v, c eta y. And this one, I just call it nu. Okay, so then you compare this one, these two, you will see I just put it here, and this is e to the power using, okay, here you exchange that to x, right? And then you will have 2v, and here you have the Gromov product at x, then you plus 2v, right? 2v Gromov product at y, and then you need to, okay, I will continue in this way, e to the power minus v, v x cos e y, and to the power e to the minus v x eta y, right? I'm correct, okay? So that's the thing there. Okay, exactly what we wrote there, this will cancel, so it's independent of x. But I can leave it as an exercise to understand this, why this guy, you look at this is independent of x. And the exercise is, you look at the Poincare disk case and try to see this is exactly a kind of geometric thing. It should be. So if you are interested in this, you can do this exercise, okay? So this is the technical proof here. Okay, now no problem. This you observe this the new defined measure actually is supported on this supported on M tutor. This one actually. So the remark is that this new is supported. Put it on this one, and because this new x is continuous, I mean has no atoms. Okay, and now I want to claim that actually this nu times dt is invariant. So now this is on M. Is, you have 2 points. One is it's gamma invariant. And the second thing is that if you apply for the geodesic flow, here I use another coordinate s. So this is also invariant. So first thing, we want an invariant measure. And this is just to show this. In this coordinate, the measure we construct, it's gamma invariant, and it's also phi s invariant. Okay. So how you show this? Actually, you just see the change in the coordinate. You will see it. Okay. So what you will see, if you apply for the first point, if you apply beta to this eta cos t. So what's the consequence? What's the consequence is you have here is beta cos c, and here you have beta eta. But because the x naught is fixed, your reference point is fixed, you will have a shift in the third coordinate. So this is t plus bx naught cos c. Yeah, I checked this. Should be correct. It's what we said yesterday. This is first point, and the second point is this phi s. When you apply to this vector V. So the S-time map of the geodesic flow, of the V under the geodesic flow, what is this one? Okay, you are still in the same geodesic, so these two are the same. You just shift it, it's very simple, it's T plus S. Okay? So now see you don't have a problem, it should be, this measure should be gamma invariant. Why? Because if you consider the value at gamma c and gamma eta, you can just choose your base point to be gamma x, because this definition is independent of x, okay? And the third point, you only have the shift problem, and here you only have the shift. So it's invariant by the geodesic. Then this measure upstairs, the measure defined in this way, we call it, maybe have a tutor here, is the, do I need to use this notation? Maybe we just don't need to. Okay, so this measure, actually you put it down to Sn, so it defines the unique probability measure on Sm. Okay? So what does it mean? I mean, this measure is called the Bowman-Margulis measure. So you will have a measure, in this way actually you define the measure on Sm whose lift gamma invariant extension to this case, to Sm tutor actually is this nu times dt, okay? So now actually we already see this measure, Bowman-Margulis measure will satisfy the entropy formula. Bm, the measure theoretical entropy of this one under the geodesic flow, T-time map of, S-time map of the geodesic flow, this guy should equals to S, absolute value, times V. See it? Why? That's what I explained. It's very similar to the Liouville measure case, but in this case, actually, you only change the measure that you see. You change the measure of Lebesgue to your measure of this, Poisson measure, pull back to the stable direction, and to see how it contracts. That's why I put it here. So if you move, because, okay, how you see it, it's the rough idea, but technically you see here, because this is independent of this x, you can let this x belong to this geodesic. So this term will cancel. You only have these two. So then you see the contraction behavior of this geodesic flow of this new x. That's what I said here. You move along this direction, the contraction behavior, the ratio is just e to the power minus v times the time. So this explains why the measure we constructed in this way has the entropy as this S times V. Okay? So this is the Bowman-Margulis measure. But since Poisson-Sullivan measure is so useful, we want to give another measure which is also related to Poisson-Sullivan measure. Okay? So what is that? This is called Robelin. Is that pronunciation is correct? Robelin? Okay. No objection. So, okay. So, okay. Yeah, do we still need this? Maybe I put it here. So this is C. Okay. So what is this measure? You define a measure. Define measure. PR or PR on this one. Okay. By setting the integral of this one compass support, this F is smooth, and this is equal to tutor, then the boundary, then fxc, d nu x c, okay, and the d volume. Okay, so we always begin with fat. So the fat is, you can check that immediately, or if you're not, it's an exercise. Okay, so this measure is gamma invariant. And the second thing is that because we already normalized this new x here, so actually it's projection to SM without a wedge here. MBR actually will be a probability on this one. Okay? So then, let's try to see the property of this measure. So properties, so we have this theorem here, which says, for any C1 vector field, Z on SM, okay, such that ZV evaluated as V, this vector, is tangent to the stable direction, the stable foliation, okay, tangent to that for all S belongs to S. This is your vector field at each point which is tangent to the stable foliation, as a stable leaf, okay, and then for any such vector field, actually you will have this identity, which says if you take the leafwise divergence of this Z along the weak stable direction, and then you plus V volume entropy, times Z, the inner product of this one with the X, this guy, dMR, V, this should be 0. Okay? So this is the first formula. And we will use this formula to understand this Berger-Roblin measure more. So you see why this is true, okay? So we'll begin with some easy thing. And so you see, of course, first, because for this problem, when you calculate this, actually we can, using this partition of unity, we only need to consider this problem locally, right? So, okay, locally, and then you calculate that. How you calculate that? You remember your MBR is defined in this way. Then you just fix x naught. Then you can, using this second relation, to express this one as the dx naught times something. And then that something we can move as a density here, then we can group these all together to be a divergence. You see this? And I just copy this. You see what I mean? Here you can, here is what? Is this quantity. I put it here. And then times what? E to the locally. The locally, what is the expression? Is V x naught C, and here you have x. And now you have what? You have the volume. I put the volume first. And then you have the new x naught C. Okay? So this is fixed. X naught is fixed, and you can fix C and consider this guy. So you consider this guy, what is this one? You look at this, it's exactly, remember the gradient of this Boltzmann function is minus x. So these two, actually, you can group that together to be the divergence of S of this Z of e to the power minus V Bx naught Cx times Z. Okay? So you're using an integration by parts. This will disappear. So this is 0. Okay? I want to convince you that this formula is important. So I give you corollaries. And more than one corollary. Okay? So the first thing is what you see about this special measure of this BR measure. Okay? So this measure actually you see will satisfy the integral of this B. B is what we defined before, right? The Laplacian of Boltzmann function, and this guy is what? This is V. Okay? Did you see it? You put this Z equals to X bar, right? That's okay. So the reason of this is you try this with Z equals to X bar. So the first point seems to be related to our topic. Okay, so this is a quantity, we promise. Okay, how about the second one? I want to say the second one is that this measure, MBR, actually is symmetric with respect to an operator, which is what? Is Laplacian S plus V times X bar. Laplacian S is the Laplacian along the stable leaf. Why it's symmetric? Symmetric means this. If in this way, for F1, F2, the infinity function on Sn. Okay, then actually you will have the integral of F1 times Laplacian S plus Vx bar applied to F2, dmr, br, actually will equal to Sm Laplacian plus Vx bar, and here F1, here F2, and dmbr. Okay, it's symmetric with respect to this one. Okay, so what is the proof? Again, you use this formula, but this time you use what? You apply it to Z equals to F1 gradient S F2. So actually you see this, once you apply to this function, you will express this as the integral of the inner product of this gradient F1 and gradient F2. So give it as an exercise. Okay, so you can see this. So this is the second corollary, and how about the third one? Okay, the third one is that this measure, MBR, actually is stationary for the Laplacian along the strong stable direction. Strong stable leaf is stationary. It's not stationary for this. Along the strong stable population. Okay. So what does that mean? Actually, this means if you consider, I should not go that far. So here, actually, you have this integral of Laplacian SS applied to any function which is smooth on Sm, smooth function on Sm. Then you consider the foliated value of this Laplacian applied to this f. Then actually this guy equals to 0. Okay, so this is the property of this BMR. So as you can see, once I put the word stationary here, actually we are already stepped into the random case. So this BR measure actually is related to what we are going to talk about. You will see that a little later. Okay. So for any f, so harmonic, that's exactly harmonic means. So this measure, if this measure is harmonic for this operator, that means for any f which is smooth on Sm, you, as far as you can take the leafwise Laplacian applied to this f, you take the integral, this is 0. Okay? So it will be related to the diffusion you mentioned. Okay? I will mention the this class. Okay. Yeah, more or less. Okay, so again, you apply to this. I can list its computations using this one, using this equation 1 again, and I put it as an exercise, but I will give you the steps. It's like this. I leave the computations to you. So first you apply, because I already checked the proof, it's correct. So first you apply 1 to this z equals to x bar gradient f x bar. Yes. And you apply to this one, then actually you will get something. I just write it here, and this gradient x bar sf. What I want to say, this function, okay, and evaluate at x, and then minus b x bar gradient f plus v x bar. I have to put it here in r is very close to 0. Okay, so then you compare the Laplacian. You split the Laplacian using the flow direction and the direction which is orthogonal to the flow direction. Actually, you will get okay, what should I say? You will have something like this. It will equals to this one. And then first you can deduce, what should I say? And yeah, you use these two things. So I leave it as an exercise here. So this one is stationary for this. So another thing here, okay, actually there's a corollary too. You see, if you apply this case to the special case, one function is constant, then what you will get, we will start from here. So actually this measure will satisfy the integral on Sm, Laplacian S, plus V x bar, applied to any function which is smooth on Sm, this integral is 0. Okay? So this class of measure is not only stationary on the strong stable direction, but is also stationary, is harmonic actually for this operator, Laplacian S plus V times x bar. Okay? So we start from here. Now we want to move on to the diffusion setting. What I'm going to talk is a family of stable diffusions. So we'll study the stationary measure. So the purpose, from now on, we will study the stationary measure. For this class of operator is Laplacian S plus rho times x bar. Okay, we will study this. We start from BM measure and study a more general case. This rho can belong to any point in this arm. Okay. So then I have to explain what does that mean by stationary measure and what's the setting here. because we already jumped to the random case now. This is our plan. So is that the first point? Is to expand this operator. So here's one definition, and we will say a differential operator L on Sm is called subordinated to the stable foliation if, if for any infinity function f on Sm, that means f belongs to C infinity Sm. Your value L applied to f and evaluated at V, this one only depends on the value of f along this weak stable leaf. This is what's a general definition. Okay. So as we said, we can always lift these operators on the stable leaf downstairs to upstairs. So in particular, this L will extend to be an equivalent family of L C on this M tutor times C. Okay, you just unfolded this leaf upstairs to be M tutor times C. That's a leaf. So, for example, the example we here is L row. We define as the leaf is Laplacian plus rho times x bar. As we see that this operator is along the leaf, and x bar is also tangent to the stable leaf. So this operator itself is its action on f only depend on the value of f along the leaf, right? Because okay. So this one will satisfy this condition, and so what does that mean? Your action of this, you can extend this to upstairs. Upstairs, then your value at f, you apply to f. This is Laplacian in y of s of fx c, y c. Evaluate y equals to x. Okay, its value at x c, and then plus rho times the inner product of x and the gradient y of this f. Again, evaluated y at equals to x, right? Okay, so this is. So what we call a stationary measure probability, we call M is stationary for this L. M is stationary L rho if what's the condition there? Let me see. Okay, I will erase this. If you have this thing as before, stationary for, or many times we call it it's error harmonic. Right? So what does it mean? It's as before, you have any smooth function on Sm, then your value, this operator applied to f, evaluated at v, right? And the integral of this one with respect to this measure will be either 0. This is your definition of error harmonic measure. Okay. So let me see. I have to explain what's the meaning of stationary. When we mention the stationary, what's the diffusion behind the first thing? And the second thing is you want to see if for this operator, for the class, this class of operator will always have harmonic measure. And the third thing maybe you are interested in is whether this measure is unique. Okay? So you already see one example is here. BMI is the harmonic measure for Laplacian S plus Vx bar, right? Okay. So then, I will explain what I said a moment ago about this, all these three things. Okay, I explain the existence first, and then I move on to the stationary thing, the diffusion behind this. So first thing is that the set of stationary measure always exists, the set for this class actually, and more general, the set of stationary measure stationary probability measures is a non-empty, convex, compact set, and its extreme point are called ergodic. Extreme points are called ergodic. Okay, so this is Ghana. You have this. Okay. So we already have example, and later I will also mention the construction. So the main purpose, hopefully today, we will see if we can go to that point. So I will give you the construction of this M rho when this rho is strictly less than B. Why? Because for rho is strictly less than V, actually this Laplacian S plus rho x bar harmonic measure is unique. In this case, it's unique. Okay? And why it's unique? There's a general theorem because in this case, the operator is weakly coercive. Okay? But I won't mention these details to save some time. Okay? So first thing, we will have such measures. Okay? So then we move on to the explanation of this stationary. And also the construction of M rho. This is what we want today. Yeah, we have some time. Good. So what's the diffusion? You go upstairs, on each leaf, on each stable leaf, then actually you will have a diffusion corresponds to the operator, Laplace in S plus rho x bar. You have a diffusion. We have probability present here, so you have the diffusion, and so we can define this as P rho x c. So we will use this p, small p, to denote the Hickenal thing on this leaf and the rho txy. Okay? So not only you define actually the stationary measure, we define it will define to this family of diffusions, leafwise diffusions of this one. And then you will have a Markov process, right? So this M is exactly even under the shift along the orbit of this diffusion. So diffusion is just like, say, for example, when this rho equals to 0, where it corresponds to the Brownian motion, right? You can visualize that as if you have never met these diffusion things, you can think that this Brownian motion is just, you have an ink here, that you see at time t what's the distribution density. This is the Hickenal, Pt xy. Okay? So stationary, maybe stationary, so that means I want to say this measure. We define this one, PV, EMV. This guy is invariant under the shift. So I will try to avoid using too many things in this lecture, because now I want to move on to the construction. We will be back to these stationary things and also the diffusions corresponding to this. But at this point, actually, even without this, you can see the construction in this way. So we want to describe of this M rho for rho less than. So, what is that? Okay, now I can follow Peter a little bit now, okay? So it makes things easier, okay? So we have notations like this. So we first, on each leaf, you have the diffusion with this infinitesimal generator, Laplace process one, with the Hickenal as small p, rho txy. Is the density that you start from x goes to y at time t, right? Okay, we have this, then we can define the Green function on this leaf, okay? Green function L rho process so this means gx c rho y c is just the probability or the probability that you start from you go to y at time t. For finite, you will arrive at y. Okay, so this is this one, and then in this case, when this rho is less equals to v, as I said, this operator is weakly coercive, so we can use this Aconna's Martin boundary thing. Theory. Applied in this case, so actually a reference is that you can look at Hampstead paper. Say for instance, Hampstead vector paper. So it's like in the hyperbolic group case, but now the point is that the geometric boundary coincide with the boundary for negative curved space in this case. So this is the point. So then we can define the Martin kernel for this diffusion. The value of this one is just the limit, that is z goes to c, and you evaluate g y c, let me see, rho z c, and yeah, I'm correct. Gx c, rho z c. Am I correct? Correct. No, here is x, here is y. So this, this z goes to c. Yeah. This is, you start from y c, okay? So that's the definition. This c is just to say it's on that leaf, has no function, okay? So this is the Martin kernel, okay? So now you see, actually, the class we want to consider, the measure is very similar to the Poisson-Sullivan measure. I mean, no, I'm saying that this measure also has a correspondence on the boundary. And this class of measure is very similar to Poisson-Sullivan measure on the one hand, and on the other hand is also related to this Martin kernel thing. It's a mixture of the non-random case and the random case, okay? So what does that mean? Let me write down the, okay, we have enough time, I think. Okay, so now for this class, maybe I put it here, because this is the definition. I want to say this is Hampstead, also the same paper. You will have, there exists a family of measures on the boundary x goes to nu, because it's also related to the Poisson-Sullivan measure. When this rho equal to v, I just put nu rho here. So this guy, x comes to n theta. There exists such family of measures. such that you will satisfy two properties exactly as before. First thing is you have beta x. This value should equal to you apply beta to this measure, right? Okay. So the first thing is this. The second thing is that now you compare the value at y with respect to the no value. These two measures, one start from y and the other start from x. Okay, and then you consider its Radon-Nikodym derivative. It's e to the power minus rho. You change v to rho now, and here you have your Boltzmann function. And you have extra term here when this diffusion thing steps in. So here you have the Martin kernel. Evaluate that one. Okay? So you will have this. And again, this family of measure is unique if we normalize it to be, the integral to be 1. So this family normalized by this one. Okay. So we have to what we will do next is to, okay, now we can describe this M rho. This is shown in this paper. You have the existence of this class of measure, and yeah, you need to do some work to make it work. Yeah, so I don't want to mention this. I want to use 5 minutes something to describe the stationary measure corresponds to this operator. So what is the thing we want to describe? Here is the, what's the harmonic measure? Apply to a small function, leafwise Sm, dm, rho is always 0. So what is m rho? I want to say that this, if we set this m rho as such as that dm rho at xc is d nu x rho c, then this m rho will satisfy what? Will satisfy that equation. Okay? So we're satisfying the integral of that one applied to, of this operator applied to f, and you take the integral with respect to m rho will be always 0 if f is smooth. So how you see this? It's very similar to the formulas we erased for the part rho equals to v. It's very similar. So let me put it here. Now you have the second equation. Almost the same. The second equation, very similar to the first one, is like this. Is you take the integral of Sm of divergence x applied to z plus rho, now here is rho zx bar, and then minus z gradient ys of the logarithm of this Martin kernel evaluate at y equals to x. Gradient is 0. Okay? This is, again, you use this property. Once you know it's of this, okay, now we only have this extra term here, right? But with this extra term here, you know this Martin kernel is harmonic for this operator. Okay? So you will use integration by parts, and also, let me see in this part if we need to use. So far, we haven't used this fact of the Martin kernel. This part is still integration by parts. Okay, so you have this one. So finally, this thing will be the divergence of S e to the power px not x times this k. So it's 0. That's the first thing. And the second thing is also similar to what we had before. Now we really want to show this Laplacian applied to f plus rho times x bar gradient f. We want to show this. So how you prove that? It's again, you use this one. You use these two. Then you apply this to what? You apply this to z x c equals to f x c times the gradient of the logarithm of k. You apply it to this function. Okay? So what you will get, let me see. Let me see. Okay. Again, this is the computations, so I want to just let me write down let me list the computations at least for you later to check it. So you apply to this one, then you obtain this f Laplacian s log k rho and plus here minus s, and this is gradient log k and gradient. Okay, So then you actually obtain this equation. I will put it here. It's F. Here you can group it to be K rho, and here Laplace in S. K rho plus this gradient F, gradient log K rho, then plus rho times F divided by K rho, X bar, and the gradients X, K rho. Okay. So then now you can use, you see, actually, you can group these two together, and then you use the property that this Martin kernel is harmonic for this operator. So Laplace in S plus rho X bar applied to your K rho will equals to 0. So this will disappear. Then you only have one term left. This integral is 0. Okay? And then you use the definition. Then you use this. You apply this to gradient F. You will see that this object will equals to the integral of this object. So it's 0. Okay? So we didn't give fundamental things today, but we already introduced this class of harmonic measure, M rho, and I show you that this M rho is a mixture of the Poisson-Sullivan measure and with some diffusion thing, right? And now the natural question is why we are interested in this class of measure. And as we promised, we will study things related to the integral of this B. And so you can guess we want to study the integral of B with respect to this M rho. What kind of property you will have and what you will see. And since it's also related to the diffusion, how about the other objects, such as the entropy and also the linear drift that you learn from the hyperbolic group case when they will come into our computations. So I will continue tomorrow. Thanks.
Rho is volume entropy. That Martin kernel term isn't there in the Radon-Nicolson derivative.
Everyone can listen to the question.
If rho is volume entropy, in the Radon-Nicolson derivative, the Martin kernel isn't there, right?
Yeah.
So why is that happening? Can you give some insight on that?
You go to the determinist case.
Okay.
Yeah.
I see.